Our solar system is an awe-inspiring place, a cosmic ballet of planets, moons, asteroids, and comets, all dancing around our sun. This celestial family has captivated humans for millennia. We've gazed at the stars, wondered about our place in the cosmos. The story of our solar system's formation is a tale of cosmic dust and gravity's pull. It stretches back billions of years to a time when our solar system was a giant cloud of gas and dust. This nebula would eventually give birth to everything we see today. Understanding our solar system's formation provides insights into other planetary systems. It helps us understand the conditions necessary for life to emerge. So let us embark on a journey through time and space to witness the epic birth of our solar system. The prevailing scientific explanation for the formation of our solar system is the Nebular Hypothesis. This hypothesis proposes that our solar system formed from the gravitational collapse of a giant molecular cloud. These clouds, vast and cold, are composed mainly of hydrogen and helium. Imagine this vast, swirling cloud of gas and dust. Regions of higher density within it begin to collapse inward. As the cloud collapses, it spins faster, like a figure skater. This spinning motion flattens the cloud into a disk. At the center, the material becomes incredibly dense and hot. The pressure and temperature cause hydrogen atoms to fuse into helium, releasing energy. This is the birth of a star, our sun. While the sun was igniting at the center of this swirling chaos, the remaining gas and dust in the disk were not just passively orbiting. The disk, now called a protoplanetary disk, was where the drama of planet formation would unfold. This disk, heated by the nascent sun, glowed with the leftover heat of creation. Within the protoplanetary disk, a remarkable process was beginning. Microscopic dust grains, remnants of ancient stars, collided and stuck together, a bit like dust bunnies under your bed. These tiny grains, through electrostatic forces and random collisions, began to clump together, forming larger and larger aggregates. This process, called accretion, is the first step in the long journey from dust grain to planet. Over thousands of years, these aggregates grew larger, eventually forming pebble-sized objects, then boulder-sized, and so on. The protoplanetary disk was transforming, becoming a swirling storm of rocks and ice, all orbiting the central star. As these objects grew larger, their gravitational pull became more significant. They began to attract nearby smaller objects, pulling them into their growing masses. The protoplanetary disk, once a relatively uniform sea of dust and gas, was becoming a more chaotic place, with larger objects exerting their dominance over their smaller neighbors. These planetary embryos, called planetesimals, continued to collide and merge, their gravity pulling in more and more material. Some planetesimals grew to enormous sizes, eventually becoming the protoplanets, the precursors to the planets we know today. This process of accretion and collision wasn't always peaceful. Giant impacts between protoplanets were common, reshaping these young worlds and sometimes even shattering them completely. The solar system was a chaotic and violent place, a cosmic construction zone where planets were forged through collisions of unimaginable power. Section 5. Worlds apart. The differentiation of planets. As protoplanets grew, their interiors began to heat up. This heat came from a variety of sources: the decay of radioactive elements, the heat generated by constant bombardment from smaller objects, and the intense pressure deep within their cores. This internal heating led to a pivotal process called differentiation. Imagine a protoplanet, a heterogeneous mixture of rock, metal, and ice. As the interior heats up, the materials begin to melt. The denser materials, like iron and nickel, sink towards the center, forming the planet's core. Lighter materials, like silicates, rise to the surface, eventually cooling and solidifying to form the planet's crust. This process of differentiation is what gives planets their layered structure. It's why Earth has a solid iron core surrounded by a liquid outer core, a mantle and a crust. Differentiation is a key process in planetary formation, shaping the destiny of worlds. Section 6. A time of chaos. The late heavy bombardment. The early solar system, as we've seen, was a chaotic place, but about 4 billion years ago things got even more intense. This period, known as the late heavy bombardment, saw a dramatic increase in the number of impacts on the inner planets, including Earth. Imagine a rain of asteroids and comets, leftover debris from the formation of the solar system, relentlessly bombarding the young planets. The evidence of this bombardment can be seen in the cratered surfaces of the Moon, Mercury, and Mars. Earth, too, experienced this bombardment, but geological activity has erased most of the evidence. While the late heavy bombardment was a destructive period, it may have also played a crucial role in the development of life on Earth. Some scientists believe that comets and asteroids delivered water and organic molecules to the early Earth, providing the building blocks for life. Section 7. Stellar Evolution, the Sun's Journey. As the planets were forming and evolving, our Sun, the central engine of our solar system, was also undergoing its own journey of evolution. Stars, like our Sun, are not static objects. They are born, they evolve, and eventually they die. The Sun, currently in its main sequence stage, is fusing hydrogen into helium in its core. This process releases the energy that makes the Sun shine and provides the heat and light that sustain life on Earth. But the Sun's hydrogen supply is finite. Over billions of years, as the Sun continues to fuse hydrogen into helium, its core will contract and heat up. This will cause the Sun's outer layers to expand, and it will eventually become a red giant star engulfing the orbits of Mercury and Venus. Don't worry though, this won't happen for another 5 billion years or so. Section 8. Planetary Evolution, from fiery beginnings to cool companions. Just as the Sun has evolved, so too have the planets. From their fiery beginnings, the planets have cooled and differentiated, their atmospheres and surfaces evolving over billions of years. The inner, rocky planets, Mercury, Venus, Earth, and Mars, experienced intense volcanic activity early in their history. Their surfaces were bombarded by asteroids and comets. Some, like Earth and Mars, may have once had liquid water flowing on their surfaces. The outer gas giant planets, Jupiter, Saturn, Uranus, and Neptune, formed in the colder outer regions of the Protoplanetary Disk. These planets, with their massive gravity, captured vast amounts of gas and dust, becoming the behemoths we see today. They too have evolved, their atmospheres churning with storms and their rings constantly changing. Section 9. A delicate balance. The solar system today. Today, our solar system, after billions of years of evolution, exists in a state of relative stability. The planets, trapped in their orbits by the Sun's gravity, continue their celestial dance. The Sun, in its main sequence stage, provides a steady source of energy, bathing our planet in the light and heat that make life possible. But this stability is not permanent. The planets, though locked in their orbits, still exert gravitational influences on each other. These subtle tugs can, over vast stretches of time, cause slight variations in planetary orbits. And then there are the countless asteroids and comets, remnants of the solar system's formation, still whizzing through space. While most pose no threat to Earth, collisions do occur, reminding us of the dynamic nature of our solar system. Section 10. Unveiling the mysteries, recent discoveries, and ongoing research. Our understanding of the solar system is constantly evolving, thanks to the tireless efforts of scientists and the incredible data sent back by robotic explorers. Spacecraft have visited every planet in our solar system, beaming back stunning images and a wealth of scientific data. Recent discoveries, like the detection of water ice on the Moon and Mars, have fueled speculation about the potential for past or present life beyond Earth. The discovery of thousands of exoplanets, planets orbiting other stars, has broadened our perspective on planetary formation and the potential for life elsewhere in the universe. The study of our solar system is far from over. New missions are planned to explore the icy moons of Jupiter and Saturn, to search for signs of life, and to unravel the mysteries of our cosmic neighborhood. Section 11. A cosmic perspective. The significance of our solar system. The study of our solar system is a journey of discovery, a quest to understand our place in the cosmos. It is a story that stretches back billions of years, from the birth of our Sun to the formation of the planets and the emergence of life on Earth. Our solar system, a tiny oasis of life in the vastness of space, is a testament to the power of gravity, the beauty of cosmic evolution, and the enduring human spirit of exploration. As we continue to explore our cosmic neighborhood, we gain a deeper appreciation for the wonders of the universe and our place within it. The journey of discovery is never-ending, and the solar system, our cosmic home, holds endless mysteries waiting to be unraveled.